Welcome to the shape of space linear algebra. This lesson is on nilpotence and the Jordan canonical form. A nilpotent matrix is a square matrix M such that m to the k equals 0 for some positive integer k. The smallest such positive integer is referred to as the index of M. I have an example here. If you take this matrix and raise it to the fourth power, you'll get all zeros. In general, any upper or lower triangular matrix with zeros on the main diagonal is nilpotent. So we could have taken this and put some non-zero numbers up in here, and then that would still be nilpotent. You may want to try that. And there's some additional examples in the Wikipedia article entitled Nilpotent Matrix, so I'll refer you to that. Then we have a few properties of nilpotent matrices. If V is an eigenvector of A, in other words, if AV equals lambda V for some non-zero vector V, then if you take A to the K times V and you keep applying this identity here, eventually you'll get this equal to lambda to the KV. So if A to the K equals 0, in other words, if A is nilpotent, then this would equal 0, and of course this would equal 0. But then V is not equal to 0, so that means lambda to the K equals 0, which implies that lambda equals 0. Thus, every eigenvalue of a nilpotent matrix is 0. The rank of a nilpotent matrix A decreases as you raise it to higher powers. So the rank of A is greater than or equal to the rank of A squared, and so on until you get to the rank of A to the J, which equals 0 for all J greater than or equal to the index. So the column space and the row space become smaller and smaller for a nilpotent matrix as you raise it to higher powers. Then finally we have a property of determinants. If A is nilpotent, in other words, if A to the K equals 0, where K is the index, then the determinant of A to the K, of course, is 0, since the determinant of the 0 matrix is 0. But then A to the determinant of A to the K equals determinant A to the K power, and that would equal 0 from this, and that would imply that the determinant of A equals 0. We have something called a shift matrix, and there's two different types of them. There's an upper shift matrix, which I'll write as U sub n. It's n by n, and it has ones along what is called the super diagonal. It's just the diagonal above the main diagonal. And then there's a lower shift matrix, which has ones in the subdiagonal, and that's the diagonal just below the main diagonal. As a linear transformation, the upper shift matrix shifts the components of a vector one position to the left. So you can see here un times this vector. It shifts everything, and it puts a 0 in the rightmost position. And every nilpotent matrix is similar to a block diagonal matrix consisting of upper shift or lower shift matrices of this format here. They don't have to be the same size. Obviously, these, I'm giving them different indices just to emphasize they could be of different sizes. And you can make similar statements for lower shift matrices concerning the shift here. You may want to try and see what happens when you do that. And as I say, you can put lower shift matrices here also. On this slide, we have a couple of theorems and another definition. Let's look at the theorem. A nilpotent matrix, other than the 0 matrix, is not diagonalizable. We'll prove this by contradiction. Let's assume A is non-zero, but it's diagonalizable. And by definition, there exists an invertible matrix P such that A equals P D P inverse. The diagonal entries of D are the eigenvalues of A. That was from Theorem 56, where we proved that similar matrices have the same eigenvalues. But as we have shown in the last slide, the only eigenvalue of a nilpotent matrix is 0. Therefore, D is the 0 matrix. Its diagonal elements are all 0, and it's since it's a diagonal matrix, we already knew off diagonal that the elements were 0. So that implies that A equals P times 0 matrix times P inverse, which equals a 0 matrix, which contradicts our assumption that A was non-zero. So we have a notation here before I define nilpotency for a function. F to the k in brackets just means f applied to itself k times. It's a composition of functions. And a nilpotent transformation is a linear transformation f of a vector space V such that f to the k equals 0 for some k in the positive integers. And then f to j equals 0 for all k, j greater than or equal to k, where k is called the index, just the way we define index for matrices, nilpotent matrices. So I have an example here. Let P sub n be the vector space of single variable polynomials of degree n or less, and let f be the derivative. So it maps from Pn to Pn minus 1. As you know, when you take a derivative of a polynomial, you get a polynomial of degree 1 less. So if we apply the derivative n plus 1 times to something from Pn, we're going to get the 0 function. No matter what we pick from Pn, we'll always get the 0. And that means that it's f, the derivative function for this particular vector space, is a nilpotent transformation, and its index is n plus 1. Okay, and then we have one other theorem. A linear transformation on a non-trivial vector space, so something that's not empty, is nilpotent if and only if its only eigenvalue is 0. And I'm not going to prove it here, but I'll give you a reference to an online book by Heffron, and it's in his book, it's Lemma 2.1, Chapter 5, Section 4. I believe he makes the online version of his book free, although I believe he asked for a contribution if you like the book. So I'll give you the link to that in the reference to this video. A defective matrix is a square matrix that does not have a complete basis of eigenvectors, meaning it's not diagonalizable. That follows from theorem 61 that we had in the previous lesson. An n by n diagonalizable matrix has n linearly independent eigenvectors. So this will happen, you'll have a defective matrix, that is, when at least one eigenvalue has a geometric multiplicity, the number of linearly independent eigenvectors for that eigenvalue, that is strictly less than its algebraic multiplicity, the multiplicity of the eigenvalue in the characteristic polynomial. So I have an example of that here. This matrix A is defective. It has eigenvalue of 1 and 2, and the eigenvalue of 1 has algebraic multiplicity 2, and the eigenvalue of 2 has algebraic multiplicity 1. However, if you work through the details, the eigenvalue at 1 has a single eigenvector, so that fulfills this condition for being a defective matrix, and the eigenvalue 2 has a single eigenvector. So by the theorem 61, matrix A is not diagonalizable. However, it is possible to find a matrix J, known as the Jordan canonical form, such that A equals P times J times P inverse for some invertible matrix P. So even in the case where you have this defective matrix, there's another type of matrix which is not quite diagonal. You'll see in a minute when I go into the details, but it gets us close to what we would like to have. I mean, we'd like to have a diagonal matrix in here for J, but as I pointed out, it's not always possible if you have a defective matrix. So in the case where we don't have a diagonalizable matrix and it's what we described in the previous slide, a defective matrix, we can still find the Jordan normal form of that matrix so that you have the matrix equals P times J times P inverse. And what I'm going to show you on this slide is the general structure of the Jordan form. Sometimes it's called Jordan normal form, sometimes Jordan canonical form. And this is the form down here at the bottom. You have these matrices. These are not single elements. These are matrices typically that go along the diagonal. And then each one of these has this format here. It can be of different sizes. And these are, this is an eigenvalue. And then this is the super diagonal with ones in it. So you can see it's almost diagonal. And then you line these up along here. I'll show you an example in a little bit. So that's the Jordan normal form. Now, even if you are a diagonalizable matrix, you'll fall into the Jordan normal form, or you'll have a Jordan normal form. But what will happen is these matrices will just be single eigenvalues, and you won't have these ones along here. So it'll degenerate into a diagonal matrix in the case where you have a diagonalizable matrix that you're working with. I have some facts on this slide concerning the Jordan normal form. Any square matrix over a field, and usually we've been talking about the real numbers, has a Jordan normal form if the field is extended to one containing all the eigenvalues of the matrix. So for R, the extension is the complex numbers, because sometimes you'll get a complex eigenvalue for a real matrix. The Jordan normal form is not entirely unique, as it is a block diagonal matrix composed of Jordan blocks. We saw that in the previous slide, whose order is not fixed. However, it is unique up to the permutation of the block. So you can just change the order of the blocks we saw in the bottom figure in the previous slide. By convention, blocks for the same eigenvalue are grouped together, but no ordering is imposed among the eigenvalues or among the blocks for a given eigenvalue, though one could, for example, order the blocks by weakly decreasing size. The number of Jordan blocks for a given eigenvalue is equal to the geometric multiplicity of the eigenvalue. The sum of the sizes of all the Jordan blocks for a given eigenvalue equals the algebraic multiplicity of that eigenvalue. Okay, so this is a lot to take in. I'm going through this for your information, and this is something you may want to refer back to this slide here. A matrix A is diagonalizable if and only if all its Jordan blocks are of size 1 by 1. I mentioned that in the previous slide. If in this case, the Jordan normal form reduces to a diagonal matrix. So that's the easy case. The Jordan normal form simplifies computations of matrix functions such as powers of your matrix, or even taking the exponential of a matrix. And we'll need some of this when we talk about in another series of lectures that I'm going to give on matrices and matrix calculus. So that's why I'm bringing it up here. We have a defective matrix A given here, and I want to focus on the Jordan form and not so much on the calculations. I used a online app to do the calculations. So A has eigenvalues 1 and 2 of algebraic multiplicity 1. And again, you need to do some calculations, but I used this app to find that. And then another eigenvalue of 4 that's of algebraic multiplicity 2. The geometric multiplicity of the eigenvalue 4 is only 1, and thus A is not diagonalizable. However, there is a Jordan normal form J and invertible matrix P such that J equals P, a P inverse. So I use this app to get the P and also J. You notice that it has 3 blocks. The first block corresponds to the eigenvalue 1, and since the algebraic multiplicity is 1, it's just a 1 by 1 block. And the same thing for 2, it's just a 1 by 1 block since the algebraic multiplicity is 1. The algebraic multiplicity of the eigenvalue at 4 is 2, and so now you get a little bit more interesting block here. You have 4, 4, then you have a 1, and 0. So the block is just this 2 by 2 matrix. Okay, so that's an example. You may want to go to this site and try some other examples. If you go to one of the AI tools like Grok or Gemini, you could ask it to give you a defective matrix of size 3 by 3 or 4 by 4, and then use that as input into this online application. Although you need to be careful. I've gotten errors for things that were not. I was asked for a defective matrix and I got something that wasn't when I use some of these AI apps, so you need to be a little bit careful. The determinant of a matrix equals the product of its eigenvalues, counting multiplicities. We have a proof. Any square matrix A over an algebraically closed field, for example, the complex numbers, can be transformed into its Jordan canonical form, shown below, this structure here. We mentioned this before, where P is an invertible matrix and J is a block diagonal matrix consisting of Jordan blocks. The determinant of A is equal to the determinant of its Jordan form J. Since similar matrices have the same determinant, we can expand that out here. Determinant A equals determinant of PJ inverse. Then the determinant of a product equals the product of the determinant. The determinant of an inverse equals 1 over the determinant of the matrix. So these cancel and you get determinant J. Let's continue with the proof on the next slide. Because J is block diagonal, its determinant is the product of the determinants of the Jordan blocks. So we can write this here. The determinant of each Jordan block, J sub I, is simply lambda sub I to the m sub I power, where m sub I is the size of the Jordan block, and the lambda sub I are the eigenvalues. And that's because the determinant of a triangular matrix is the product of its diagonal entries. So this here, determinant J sub I equals lambda sub I m to the m sub I power, where again these are eigenvalues. And then taking what we had from the previous slide, this here, and then what we just set up here, we get the determinant of A equals the product of the eigenvalues raised to the appropriate powers. That takes into account algebraic multiplicity. I want to conclude this lesson with a couple of examples on the Jordan normal form. What does the Jordan normal form look like for a 6 by 6 matrix, which we're not given, but we're given that it has an eigenvalue 1 with algebraic multiplicity 1, and since the geometric multiplicity is less than or equal to the algebraic multiplicity, the geometric multiplicity would be 1 also for this eigenvalue. And then eigenvalue 7 of algebraic multiplicity 1, and by implication geometric multiplicity 1. And then a third eigenvalue, 11, of algebraic multiplicity 4 and geometric multiplicity 1. So I copied down the rule from earlier in this lesson. So we'll use that to construct the Jordan normal form for this matrix. The number of Jordan blocks for a given eigenvalue is equal to the geometric multiplicity of the eigenvalue. So each one of these 3 eigenvalues has geometric multiplicity 1, which means we're going to have 3 blocks. The first 2 are easy because they're just algebraic multiplicity 1, so the size is just 1. So we have a 1 by 1 block with a 1 in it, and a 1 by 1 block with a 7. And then the third one, there's 1 block, and the size of it is the size of the algebraic multiplicity, so it's 4 by 4. And then using the rules for constructing a Jordan block, we have 11s down the main diagonal and then 1s in the super diagonal. So this is the Jordan normal form for our 6 by 6 matrix given these conditions. In the previous example, what if the eigenvalue 11 has algebraic multiplicity 4, but geometric multiplicity 2. The Jordan blocks must account for the difference between the algebraic and geometric multiplicity with the following implications. This is based on that rule I copied on the other slide. The number of Jordan blocks for the eigenvalue at 11 equals the geometric multiplicity. So there's going to be 2 Jordan blocks corresponding to this eigenvalue. The sizes of these blocks must sum to the algebraic multiplicity of 4. So that gives us 2 ways of making that happen. We could have one block of size 3 and one block of size 1. That's what I have here. And the Jordan blocks for 1 and 7 are the same. We didn't change anything on that. So we have this one of 3 by 3 and then a 1 by 1 block for the eigenvalue at 11. Then we could also have 2 blocks of size 2, and that's what I have here on the right. So these are the 2 possibilities. Since we were not given the original matrix, there's not sufficient information to determine which of the 2 possibilities is appropriate. They're not both going to work for a given matrix, but as I said, we're not given that. So what you need to do, and I'm going to leave this as sort of a research project for the listener, you need to determine what's called the minimum polynomial. It's a polynomial that divides the characteristic polynomial, and sometimes it has lower powers for the different terms, and that's what gives you a determination of whether it's this or this Jordan normal form. So I'll give you a reference here to the minimum polynomial. It's a Wikipedia article, and of course you can look that up in other places too, but this is one place where you can get some information. As I say, it's sort of a research problem to figure out how you go about finding the minimum polynomial, and then how do you apply that to getting the Jordan normal form. Okay, so that's it for this lesson. I have one more lesson in this series, and then I'm going to have several more entire series, one on matrices, one on matrix calculus, another one on tensors, another one on the Perron-Frobenius theorem, and then one on Markov chain. So quite a few more coming, and they're all based on a book that I've written a draft of, and I'm using these videos to help me proofread my book, and also I just wanted to make this information available to better support the book. So hopefully you're looking forward to these lectures, and feel free to comment or give it a thumbs up in on the YouTube page.